and plug a camera in and get back to learning discrete math. Awesome. So last time we were working on this interesting claim. I'm just going to write it out formally. I'm not going to make us go through that song and dance. And we're still working on, like, basically divisibility. Did I spell that right? Divisibility. Look how many I's there are in that. Oh my God. What's that? 1, 2, 3, 4, 5 I's. Crazy. There definitely is an I in divisibility. This is divisibility proof. So this is like 4.3, 4.4-ish. So our claim was, I already want that room back. Our claim is that for all A in Z plus and for all B in Z plus, A divides B and B divides A if and only if A equals B. So that's our claim, and by the way, we should note that Z plus, these are just positive integers. So by the way, Z plus equals the natural numbers, because natural numbers are just integers, but you start at 1, so you start positive, right? So Z plus equals natural numbers. I'm just introducing some new notation. We sometimes call them this because also Q plus is the positive rationals, R plus is the positive real numbers. So it goes like that. So this was our claim. And last time we talked about how to prove it. But let's just, real quick, work on this again. Remind ourselves where this comes from. So first of all, which way do you think is easier? To go from the left to the right or the right to the left? Because it's a biconditional, so we have to prove both ways. So left to right or right to left? Any guesses?
Let's go with left to right.
Left to right. So we can do both ways, right?
Okay.
But say right to left is easier just because, check this out. If we're going this way, so we're going right to left, A equals B. So number one, that means that A equals B times 1, which by definition, that makes A a multiple of B, all right? So B divides A. Or we go the other way around, B equals A times 1, for example. So that makes B a multiple of A, so A divides B. So that's really easy, right? If A equals B, clearly A divides B and B divides A, right? That's just saying that a number divides itself, which it does. That's saying a number divides itself. It's just saying that twice, really. It's saying the same thing twice in a certain sense. So, yeah, that's all that's saying. So that way's easy. This way's harder, though, right? If we start off with the fact that A divides B and B divides A, how do we know that A is gonna equal B? Why couldn't there be some weird A and B where A divides B and B divides A, but neither of them, but they don't equal each other? That's the real question. And in my opinion, it all comes down to this fact right here. And that is, notice, if 1 is less than or equal to K, right? Then A is less than or equal to AK. Yeah. And this is just by multiplying on both sides by A. Because recall, this is like an inequality fact you're allowed to know, right? recall that, for example, like 5 is less than 7, and then 5x is less than 7x if x is what? For example, so for example, right? This is these are some like inequality algebra rules, right? If x was 2, this makes sense, right? 5 is less than 7, and 5 times 2 is less than 7 times 2. That's saying that 10 is less than 14, which checks out.
Is it when it's positive?
When it's positive, exactly. Because you start multiplying by a negative number. Well, 5 times negative 2, is that less than 7 times negative 2? That would be saying negative 10 is less than negative 14, which is not true. Negative 14 is to the left of negative 10 on the number line. So negative 14 is actually less than negative 10. It's more negative. The point being, you flip it if it's negative. If you multiply a negative, you flip it. So 5 less than 7 is that will imply that 5x less than 7x if x is greater than 0, meaning x positive. And it goes the other way. You flip it if x is negative, right? The point being, this applies to anything, right? As long as a is less than b, then ax is less than bx if x is greater than 0, and ax is greater than bx if x is less than 0. X is negative. These are just inequalities. So the point is, that's why this works right here. Why is this important? Well, it's important because, I mean, think about it, right? If, let's look at a case of division, right? Like A divides B says that you can divide B into groups of A, into integer groups of A, right? Like, for example, if you had like 1, 2, 3, 4, 5, 6, 7, 8, right? You can divide 8 into integer groups of 4. Oh, I miscounted. There you go. The whole thing's 8. You can divide 8 into 2 groups of 4, an integer groups of 4, right? That's totally fine. But can you divide 8 into any integer groups of size less than or more than 8? Like, could you divide 8 into groups of 9?
Not if you want it to remain integers.
Not if you want to remain integers, right? But you 8 into whole number groups of 9, right? I mean, I guess you could divide it into like a fractional thing. We're talking about integers here. The point is, I mean, this should make perfect sense, right? A divides B. This should mean that A is less than or equal to B. And B divides A. This should mean that B is less than or equal to A. And once we prove that, well, if A is less than or equal to B and B is less than or equal to A, that means that A must equal B. Does this make sense right here? Just this part in purple, at least. I hope so. I think that makes sense, right? Because if A is less than B, less than or equal to B, I mean, A less than or equal to B, but B is less than or equal to A, that means that's also less than or equal to A. So that means B is between A and A. And since A and A are equal, the only thing between A and A is A. Ooh, this rings of the squeeze theorem. Who loves that? But anyway, how do we show? How do we prove? We need to prove that A less than B implies A is less than B. And here's how we do it, right? A divides B. By definition, that means there exists a K such that B equals AK, right? And because we're dealing with positive integers here, and so if they are positive, K is going to be positive or negative?
K has to be positive.
It's got to be positive, right? If k were negative, since a is positive, a negative times a positive would be a negative, meaning that b is negative and b is positive, right? So k's got to be positive too. The point being, k is positive. So k is an integer by definition of divisibility, and it's positive. So k is a positive integer. Notice, what's the smallest positive integer?
Is it 1?
Just 1, right? I mean, if we look at the integers, we have 0, 1, 2, 3, 4, -1, -2, -3. These are the integers. The positive ones start here. 0 is not positive. It's because it's not greater than 0. It's just 0. And these are the negatives. The point is, the positive integers start with 1. So 1 is the smallest positive integer. Meaning, if k is a positive integer, 1 is less than or equal to k. Hey, that makes sense, right? It's just the smallest positive integer it could be. But if 1 is less than or equal to k, here's what that means. That means that then, so I'll say then, 1 is less than or equal to k. So, if we multiply both sides by a, which we can do because a is positive, so we don't want to flip the inequality, we get that a is less than ak, less than or equal to ak. And what does ak equal? What b? So this means that a is less than or equal to b. So, and this makes sense, right? What we basically just done is prove our intuition that if a divides b, a biggest a can be is b. A's got to be less than or equal to b, because you can't divide b into groups of a if a is bigger than b. And it makes sense. And we do the same thing over here to get that b is less than or equal to a, because if b divides a, b's got to be smaller or equal to b, or b's got to be smaller or equal to a. And if a divides b and b divides a, as we talked about, we can put those together to get that a equals b. Does this idea make sense? Once again, all we're doing is showing that if a divides b, and b divides a divides b means that a is going to be less than or equal to b divides a means b is going to be less than or equal to a. Therefore, we're good.
So if we're doing a formal proof, for that very last bit, we would just say by squeeze theorem, a equals b.
It wouldn't say by squeeze theorem. This is one of those.
We just know it, sort of thing.
Facts you're about to. Well, it's one of those facts with the integers you're allowed to know, and that is, if a is less than or equal to b, or is less than or equal to a, then a's got to equal b. So the fact about the integers that you're using is that there's no integer between a and a, right? Like there's no integer between 1 and 1, or between 2 and 2. Which is like really obvious, right? But I guess it's like a fact you're using. I mean, I see what you're saying. Like, what do you cite as what you're using? Yeah. So this is a fact with the integers you're allowed to know. One of those, like, you're allowed to know that like a half isn't an integer. You're allowed to know the integers are close under multiplication, that kind of stuff. Good question though.